What I liked about Vijay's talk is it shows one of the key attributes of SDN in that he's built 3 sample domain-specific networks using the same architecture and the same pieces of hardware, right? Open flow switches, open flow controllers. So that's really encouraging. The next talk is about an open flow controller that's really easy to modify because it's written in Python and thus a good piece of software to use for that approach. And I'd like to remind you that the Twitter hashtag is NSWAU17. There's a photo of me on that earlier, and my children have already paid me out, so there's no reason for you to miss out. I'd now like to introduce Brad Cowie from Waikato University in New Zealand. I'd like to thank Brad for making the trip. Thanks, mate. He looks after the infrastructure at WAND, which is the research group at Waikato in their computer science department. He's keen on automation, obviously, as is everyone. He's doing research in the software-defined architecture. He's working on the Faucet software, which is an open source SDN controller project written in Python. I'd also like to welcome Josh Bailey from Google, who's had something to do with that project. You can meet them both again at the demonstration at 5 p.m. and have a drink and chat to them. All yours, mate.
All right, thanks for the introduction, Glenn. Yeah, my name's Brad, and basically I run OpenFlow networks is what I do. And today's talk hopefully will feel like it fits in with what Vijay was saying and what Phil was saying before. I've sort of targeted it at, this talk is running OpenFlow enterprise networks, which is hopefully what will click with you guys. And yeah, I'll hopefully convince you of some things today. So basically, this Faucet word's been bandied around quite a bit. Now, this talk isn't a marketing talk for Faucet. I'm going to keep, I'm not going to list every feature we've implemented, and I'm not going to give you like a standard vendor talk. We're trying to do different things. So basically, all I'm going to say is we are open source. We test ourselves very well, and we consider that one of our core philosophies. And we're deployed in production, so we call ourselves a production SDN controller. Primarily, most of our development happens in New Zealand, but we have something in the order of 30 contributors, and a lot of them are overseas. We basically program data planes, so switch with the standard API OpenFlow, and we also integrate with standard networks through just standard network protocols. So we're not, that's how we get around the bootstrapping problem of, how do I roll out an OpenFlow network? Do I have to buy a replacement one of everything on my network and roll it out? No, you can just plug our network into your regular network and it just goes. We support multiple vendors with a single pipeline, which is one of our very key ideals we've had from day one. So what does that mean? It means that we don't have a driver abstraction layer to program different switches in different ways. We just have one pipeline and we get vendors to implement that pipeline, and that lets us implement all our features in the same sort of quality on all devices. And you don't have to worry about when you buy a new device, is this feature going to work or not? We test that. We also are very keen on network monitoring. So we have a gauge component that does all your monitoring for you, and that'll be talked about later. And I can't stress enough how much we put importance on being easy. So I just like to iterate that, you can install us in less than 30 seconds. So that's most of what I'm going to talk about Faucet out of the way with. Now I'm going to talk about my network that I run at my office for my researchers and students. And I'm going to show through example why you would want a network like this. And just keep in mind that it's all implemented in Faucet. So basically, we run our own network at my research group. And that's just because that lets us to be very agile, and it lets us do things that our core university has been slow to uptake themselves, like BYOD, and we don't really fit in with most of the other people on our campus. We're not part of the cookie cutter mold. We do a lot of weird network stuff, and so it's easier to have our own network and do the weird stuff there and keep it away from the campus firewall and stuff like that. So before we had a Faucet network, we had this very simple network, 4 Dell Power Connects plugged into each other and a Linux router. I, manually typed away things on the keyboard and made it work. And I sort of got sick of this, so I work on Faucet. I thought, we should probably deploy that and use it ourselves. So I decided to replace it with a multi-vendor SDN network, and so this was a few months back. So the benefits being, I don't need to type on a keyboard anymore, as much. I didn't have any monitoring of the previous network because I don't really know how SNMP works. That's way too hard for me. So I wanted to make that work. I wanted to add a lot of network policy, which is one thing I didn't do before. Everyone could just talk to everyone, and it was a happy party. Had no resiliency, so we were aiming to fix that. And yeah, key thing to dog food. So this is the diagram we sort of came up with. Network engineers like diagrams, and hopefully this bottom part makes sense. So we have a access layer, which is where we get all our ports, and they connect into a series of switches at our aggregation layer. And so you notice we've got 3 different vendors in there: Allied Telesys, Cisco, and HP. So all of these are OpenFlow controlled, and that's via this control plane network that we have hanging out the side. At the aggregation and access layer, we're doing our forwarding, and that's also where we implement policy. So basically, we can define policy at that ingress port when someone plugs in, so we can very effectively drop things before they get anywhere near the network. The thing that you might not be used to is this part here. It's basically a Linux server, and it runs Open vSwitch, which is a very high-quality production OpenFlow switch written in C. Basically the benefits of running this here is we got lots of memory in this machine and lots of CPU, and that's very cheap to purchase. So this is where we're implementing all of our services. So Faucet runs in here in a VM, and then that's what controls everything. Gauge is our monitoring thing, that runs also in a VM, connects to Open vSwitch and then onto the network. And then the services I'm going to talk about later are the cool things. And so this is where routing happens on this box. We do BGP pairing on this box. We assign addresses and stuff like that. This is all running through a thing called DPDK, which is Intel's data plane development kit. And that gives you like raw access to the NIC, which lets you be very quick. I've been very happy with Open vSwitch and DPDK. So this is what it looks like. So basically, access layer on top and the aggregation layer on bottom. I didn't get a good photo of the Dell server because it's in a dark, dingy rack. But this is 248 OpenFlow ports. We basically have black as the control plane, yellow is VLAN trunk, and things plug in and lights blink. So that's pretty good. So what are some of the cool things we're doing with the network? So basically, there's this thing called Ansible, which you may or may not have heard about, which is, I joked this morning, bash scripts as a service. It will SSH into something, run Python, and it will copy files around, it'll do templating, it'll automate your configuration, basically. And I sort of said at the start of this project, I had this goal of, if we could put everything in Ansible, which is just text files and scripts, and we put that in Git, then so Git's a versioning control system, every commit in Git is now a new network state. So the network switches are configured through Faucet, so that's a YAML configuration file, so that you put that in Git. You put all your service, your VM definitions in Git, you put your Open vSwitch config in Git, you put everything in Git, and now every commit is new network state. So what does that mean? When you do a new commit, you have a diff to the previous commit. That makes reviewing really easy. You give it to a colleague and go, I propose we change these things. And someone can look at that and go, yay or nay. Rolling back is super simple. If you have a problem, you go back to the previous commit. It also means there's some really cool things in Git, like Git bisect, so you can go, this commit didn't work, this commit did work, and it will find the commit in the middle that caused the problem. So there's lots of fun stuff like that. Ansible also has this thing called inventories. So basically, you can go, here's my production machines, and then here's a copy of them, which is my staging machines or testing machines. And so since it's all OpenFlow and SDN, your staging and testing could be Open vSwitch configured in the same topology running on a server. So that means you can roll out to there first, test it works, and you have more confidence before you roll out to the real thing that's going to work. You can also implement like canaries. We have a small part of the network that you roll out to first, and for my instance, that could be my desk, And if I can still log into a server, that means everything went well. If not, then I should probably roll back. And basically, as part of the Ansible playbook, which is the set of things that applies, you can also do stuff like test the config looks sane. So before anything gets rolled out to the network, we check, does the syntax look right? Because someone mentioned before, what happens when you miss that semicolon and it rolls out to 1 million machines? Well, you can test for that. When I say, you want to test these things, automate that as well. And when you've automated your testing, which is exactly what Phil was saying before, you can do this thing called push on green. So if your test environment looks clean, if your canary looks clean, just auto commit that network to config to the network. You should be pretty confident at that point that it's going to work. If you're not confident, you should probably go fix your tests to make sure that they are doing the right thing. Because automated tests are always going to find stuff that humans don't. I can very much attest to that. And by the way, I put all this on GitHub, so if you want to see my network live, there's a link at the end of the slide. So yeah, testing is, if you haven't got the point yet, it's really important to us. So Faucet has this test suite, and I think we're up to about 139 different tests, but basically every time we implement a new feature, there's a new test that goes in to test that feature works. Every time I find a problem in my network, I make a test, someone makes a test, and we know that that's never going to happen again because we test for it. So our test scenarios, basically, in Faucet, you've got a hardware test suite and software test suite. It's the same test suite, but you can run it on your desktop or in a VM or something against software. So that means, every time someone makes a commit to our project, the code goes through that test suite, so we know that it's good. But you can also run against hardware switches as well, the exact same test suite. And so what does that mean? So I implement tests to make sure they're going to work. It also means you can qualify your network kit before you get it, or before you deploy it, rather. So I don't know how many of you guys have purchased equipment before and you spend hours parsing out the vendor documentation. Does it do RFC blah? It really needs to do RFC blah. Does it implement it in the right way? What we've done to work around that problem is you just get a bunch of switches, plug in the test suite, and it says, good, it supports everything you want on your network, or bad, it doesn't. And you can send that output to the vendor and you can go, why don't you implement this feature in this way we expect? So this means you can automate your RFP process. I really like automation. So network visibility is one thing I'm very keen on. So I didn't want to spend too much time on this. Let's not reinvent the wheel and make our own network monitoring system for Faucet. There's a lot of great work that's gone into this area already. So I did a lot of network monitoring before I was on Faucet, and there's a lot of great projects. So at the moment, we're using 2 different collection / sort of storage systems for our data. So if you don't know, for visibility, you want to collect absolutely everything, and just when you've got time, wade through that and make a good way to visualize that to check it looks good. So we're using Prometheus, which is, it collects data and it also lets you write rules to match problems in that data. So we use that for things like our MAC table. So we have a centralized MAC table that gets stored in that. We keep port state in there. OpenFlow channel utilization, so it's very important to watch that so that if you have too much traffic on your control plane, basically you sort of start to DOS the network from itself. So we are very keen to monitor that. You can also do something that you can't do with regular hardware, and that we can start to instrument ourselves. So we can count, in Faucet we've got some loops like when we resolve hosts, we go around a loop and resolve them all. And we can make a new metric for how heavy that is on the system. And you can put all this into your dashboards and you can watch what actually the software is doing, because it's all open source, right? We also use InfluxDB, which is just a basic time series database, where you put your traditional port counters, bytes in and out, errors. That won't be too revolutionary to everyone. And then what we do is we have Grafana on top of this that provides these pretty real-time graphs that you can look at. And so I'll show you one here. So this is an example of basically where the spike is. Ooh, dear, wrong green button. What the spike is here is us deploying new code. So when we deploy new code, there's a few things we need to do, so there'll always be a spike there. But you'll see here, we've got this sort of line, and you'll see after we deployed the new code where we were fixing, so this is packet in, so this is packets from the switches up to the controller. You'll see we've heavily reduced this. So this is a way of verifying that the feature we wrote worked. Another example here is this is a real-time dashboard of how many hosts on my network. So we collect at the moment every 15 seconds all metrics on the network, and you can just have this on your desk scrolling past in real time. So this is just the one I have on my desk for how many people in the network, and if any of these sort of dip down, then I should probably go look at why everyone's leaving the network. So one of the big things that is super interesting for me and probably people in this audience is implementing services. So because we've got this server on the network now that has many core Intel Xeon processor or something, we have a lot of compute now where we can do things. We don't need to buy a network appliance, plug it in somewhere on the network, and worry about how to make it redundant and how to get good power to it and blah, blah, blah. We just spin up a VM for it, right? And all of these are defined in Ansible as well. And I think Phil said before, how long does it take for Brad to spin up a service? So the answer is probably about an afternoon is the quickest I've spun up one of these things. So the services we're running at the moment is, wrong button again. So one of the services, so Wand, we still do quite a bit of network monitoring, so we have our own network monitoring system. That's just a VM. Catalyst IT, a Wellington company who's actually here and speaking next, we run their DDoS monitoring system. That's open source. You just deploy it, and hey, now I've got instant DDoS monitoring. One of the kind of cool things about my network I like is I've got a VLAN that is IPv6 only, and by that I mean I drop everything that is not Ethertype IPv6. There's no ARP, there's no nothing. And that is a OpenSSID in my building. There is no other OpenSSIDs on the whole entire campus, but this is the one. And it's sort of my mission to get people using IPv6 and show it works. And one of the services I run is NAT64, which lets you translate very simply v6 hosts onto the v4 network. And for about 95% of cases, that works fine. So my phone lives on a v6 only network at work, and it's pretty cool. So we're also running, your standard DHCP server to give out addresses, Birds there for BGP, and these are all just VMs. They hook into Open vSwitch, and you just spin these up as you want. So another really big thing I told you I was going to mention is policy. So policy is how you do, how you enforce things. So Faucet has this idea of an ACL, and basically an ACL matches whatever OpenFlow can match, so TCP ports, ether types, MAC addresses, whatever you want. And this is user supplied, so this is how you control Faucet. You put in an ACL. So an ACL has a match, and then it has an action. And so at the moment we can do drop and allow, which is firewalling type stuff. We can do output, so that's something I'm going to mention a bit later, which is policy-based traffic inspection. And we also do modify, and that's useful for doing we can carve packets off and send them at a host that's dedicated for that traffic. So for like 802.1x, which is our demo you can come check out at 5 o'clock, we can carve off EA poll packets and we can send them to a host that's dedicated for processing those. And you can modify the packet if you need to add some auth data or something. So that's how you do DHCP and DHCP option 82 and stuff like that. ACLs are implemented in two ways at the moment. So we've got port-based, so that's you can configure per port. So that's so on my network, that's how I'm doing DHCP spoofing. That's how I'm implementing IPv6 router advertisement, which is notoriously difficult on vendor devices, but it's actually really easy to write just the policy to do it. That's how I'm doing BCP38 as well, so stop people spoofing IPs. It's an FV offload I mentioned before. VLAN-based ACLs as well. You can put an ACL on a VLAN, so that's a very efficient way for a large number of hosts, applying a single policy. And now here's some examples of how I've used these policies on the network. So I also have a day job. I don't just write Faucet all day, and I do a little bit of consulting work with our central IT at Waikato University. And I did incident response on a couple of things. You might have heard of them, and you might have had to deal with these. So Intel AMT was this great feature in vPro Intel processors where you don't buy a password and you have KVM access to everything on your network if you made the mistake of enabling it. And there was the WannaCry Samba stuff. And when I was doing incident response for these, I sort of realized how restrictive these central firewall architectures that most campuses roll out are. Only packets that go through there can be firewalled. And if you have too many rules, you're probably going to bog down your central firewall, and it's going to make it hard to filter these things. But with Faucet, what you can do is at the bottom here, I've got an ACL I wrote, and it drops AMT traffic, so you don't have this vulnerable KVM thing on your network anymore. And so there's a few more ports that get dropped, but basically that gets applied to every port on the network. And with Faucet, it's pretty much instant to deploy that, and you've stopped it now, right? It can't actually go on the network because we have the port-based at the access layer. Another cool kind of thing is this sort of policy-based traffic inspection I mentioned before. So we can use an ACL to match traffic, and we can send to like an NDASTAG capture card or something like that. So instead of doing your inspection on big links, so people usually do all their inspection on their sort of core links because then you don't have to buy as many capture cards. But now you're looking at 10 gig, 40 gig, and it's pretty difficult, especially when you're only looking for a particular user or a particular traffic flow. So what we can do is we can carve things off from a big link, and you can just look at that. So you can kind of think about it as TCP dump running on your switch, because it all happens in hardware and it's all very efficient. And basically what you do is you plot some capture cards across your network, and you just steer packets towards the one that you want to look at the traffic. And the reason why I mentioned index DAG card is because you can also signal the DAG card with metadata about what it's capturing. So you can say, this is the rule that matched this stream of traffic. And you can also, because Faucet's like a central controller, and if you're doing some auth there, you could inject this is the user that was doing that as well, which I think is quite cool. So this is just at the bottom a very simple, you carve off TCP traffic and send it to a DAG card. So future plans. So Faucet itself, we're sort of giving ourselves a bit more structure at the moment. So we're going to start a Faucet Foundation in New Zealand, and that's open for internationals to join as well. And basically that's going to give Faucet a sort of a group that looks after it and makes sure that we're hitting the right track, and we're going to maintain our open sourceness, and we're going to be committed to our users and developers. So if anyone's interested in joining, it's free to join, and we'll be up and running in a couple of months if that interests you. I'll be adding policy-based routing to the network as well. So that's just, you take the ACL concept to picking your next hop. And another thing that you may be interested in is wireless and what you can do with OpenFlow there. So wireless APs are interesting in that you probably have thousands of these deployed across your network. And what's an access point? It's a bridge, right? It bridges wireless to wired. So it's a switch. So you have 1,000 of these switches across your network that you don't control in any fashion apart from checkboxes in some web interface. So Allied Telesys make this cool OpenFlow access point product that lets you have Faucet controlling that bridge on the switch. And so you could implement your policy on that bridge. So instead of having this device you don't control that's going to eat all your multicast or broadcast, or if it's trying to do client isolation, it rewrites all the addresses. You can control that and decide what it does. So a big thank you to, it wasn't just my time that went into this project of building the network. The Faucet developers put in a huge amount of work. I think between our last two versions, so the current version that's deployed and the one previous, we went through around 600 commits of code. So I think Vijay was saying, the Silicon Valley thing, yeah, we kind of do that. We write a lot of code. Big thanks to the vendors that were part of the network. They either provided bug fixes or equipment. A big thank you to Rians, who sponsored us ASN, IPs, and bandwidth. AARNet for inviting me. I hope this was interesting. And thanks to my group for providing my time, I guess. And a challenge to anyone in this room. If this sounds interesting to you, or if any of this resonates with you, less than 30 seconds. Pip install or run us with Docker. Done. Really easy. Have you got any questions? So this URL at the top is all our dashboards are public and live. This is the real running network. You can look at the DDoS inspection. You can look at my Grafana dashboards. There were more I didn't show today. Those are all there. All the Ansible's on GitHub, which is available at that link. But otherwise, come see me. We've got the demo stall with 802.1x. That's my email address. Or if you want to learn more about Faucet, that's how you get in touch with Faucet. Thanks.